Another example using Newton's second law for rotation, which is right there. Up at the top, sum of the torques is I alpha. That is Newton's second law for rotation, as introduced in the last video. And remember also the definition of torque there, which always is going to be useful. So I'm going to take a situation here which might not at first seem like a rotation. Everything we've talked about rotating so far is something that sort of fits into our normal category. It's sort of obvious that they're rotating. Things like a ball spinning, or a top spinning, or a hula hoop moving across a yard. Obviously it's rotating. Wheels are turning, right? A globe spins. A spool with thread on it might spin if you pull the thread off. These are all things that very easily fit into our preconceived idea of what rotation is. But here's one that may not. I'm going to demonstrate for you. One of the things about doing physics this way is I can't do quite as many demonstrations. It's not easy to schlep all the stuff over here from the lab, and it doesn't come across quite as well when you're not physically present anyway, so I've not done a whole lot of demonstrations, but here's one live for you. Here we go. I'm going to hold my arm out, I'm going to let it drop. You ready? 3, 2, 1. And see it again? I'm going to stick my arm out and let it drop. 3, 2. There you go. That was a rotation. The arm started off pointing to the right, ended up pointing down. It rotated around an axis right through my shoulder, right here in my joint, right? That's a rotation, right? From like 3 o'clock down to 6 o'clock, right? Like the hand of a clock rotating. You might not normally think of that as a rotation, but it is a rotation. And so what I want to know is how quickly did my arm accelerate? Okay. Now, my arm's a complicated thing with all the bones and the muscles and so forth. There's different densities in different places. It's kind of soft on the outside, kind of hard on the inside. So it's a complicated thing, and it bends and moves around a lot. But for the purposes of this question, what is the angular acceleration of my arm? We can model my arm in a simpler way, as simply a long, uniform, like a post with an axis right there at the end. Okay, so we're going to hold this end firm. This is our axis right there. Let me write it up here. That pink point right there is our axis. Okay. And that point is going to stay still while the rest of the arm turns. And so instead of my arm, we're just going to think of like a piece of wood or something here with the same mass and dimensions as my arm. So a rough model of my arm. And we're going to ask what happens if we release that, right? It's going to fall, it's going to swing down. I'm actually going to put this length is 0.74 meters, which is about as long as my arm. 0.74 meters, we'll call that L. We're going to let it fall. Okay. So, how do we draw the forces on my arm? What force is doing this? You want to see it again? What force is doing this? It's gravity, right? But gravity works at all points on my arm. My fingers, right? My thumb, my hand, my forearm, my upper arm. Gravity is working elbow everywhere. What we do, and this was a subject actually at the end of chapter 9 that I passed over. We treat the arm here as if this is a uniform beam, and we use what's known as the center of mass. Okay, center of mass, CM. For the purposes of the motion of this beam, we can treat this beam as if it is all concentrated at the very center of it, at what we call the center of mass. And if it's a uniform beam, then the center of mass is at the very center of the stick. Sort of like this meter stick I've got here. Here's a meter stick, right? This meter stick is a uniform beam, right? So we're going to model my arm like this beam dropping. Well, the center of mass of this stick is right at 50 centimeters. Right at There, right at 50 centimeters. It's the point at which I could balance it, right? Wait, let me see. It's the point at which I could balance it. Right, so I'm right at 50 centimeters and it's balancing. Actually, it's a little bit more than balance. Let's see. There we go, something like that. Okay, so I'm right at 50 centimeters now. I am holding this at the center of mass. And we can treat the motion of my arm as if all the mass is concentrated at the center of mass. So we can treat my arm as almost like a point particle with all the mass concentrated halfway out. So we say that's the point at which gravity acts. So gravity is going to be pushing down on my arm that way. That's the force that causes the rotation, right? That's the force that causes the rotation. Okay? And the question is, I didn't write it up here, but the question is, what is the angular acceleration of my hand, rather of the beam, okay, of my arm? What is the angular acceleration of it? And also, what is the initial tangential acceleration of my hand? I want to know alpha. I want to know the angular, the tangential acceleration of my hand out here at the end. Okay, and we're going to treat the gravitational force on my arm as if it's all acting at the center of mass point right there, straight down towards the center of the Earth, down the direction that gravity always points. And we're going to apply Newton's second law for rotation in order to find the angular acceleration and the initial tangential acceleration. Here it goes. Let's do it. Sum of the torques is I alpha. Okay? So let's see. I think I'll do it right down here. I'm going to do it in white. Sum of the torques equals I alpha. Well, what are the torques? There's only one force acting, and that's gravity. And it acts at the center of mass. Not at the end, not here at the axis, but at the center of mass of my arm, which would be about right here somewhere. In our model, using this stick as this beam as a model of my arm, it's right in the middle. Gravity acts down on it. So remember that the torque is going to be the force times the moment arm, rather the magnitude of the force times the magnitude of the moment arm times the sine of the angle between them. So the force here is mg. Okay. What is the moment arm? Well, the moment arm, remember, is a vector that runs from the axis to the point at which the force is acting, which is for us the center of mass. And we'll see the center of mass thing again and again over the next week. Okay, this last week of class, you'll see it over and over again. So that's our vector r. It runs from the axis to the point at which the force acts. And the force acts, we say, at the center of mass. So what is the magnitude of r? Well, it's half of L, right? L was 0.74 meters. Center mass is in the middle of the beam, so that's going to be L over 2. This is our force. This is the magnitude of our moment arm. And then sine of what angle? Class? Correct! 90 degrees. Again, there's a 90-degree angle between the two. That will not always be the case. We'll do an example in a couple videos from now where the angles are not 90. But for now, they're 90, so it's going to be sine of 90. And as we said before, what I said in the last video is still true. The sine of 90 is still equal to 1, which is nice. Now, is this a positive acceleration or a negative acceleration? I mean, or is this a positive torque or a negative torque? It's a negative torque, right? It's a negative torque. So we're going to put a negative sign out in front because this force tends to rotate my arm in a clockwise direction. Clockwise is negative. So it's a negative sign out front. Okay, that's the left-hand side. The right-hand side In a situation like this, when you have a beam rotating around a point at its end, turns out that I is equal to 1/3 ml squared. If you go back and look at page 316, table 10.1, you'll see that if you have a stick like this rotating, not around its center, not like this around its center, but around a point at its end like this, right? A point at its end like that, the moment of inertia is 1/3 ml squared. And again, as I've said before, that will be given to you in a COL. You won't have to know that stuff off the top of your head. ml squared times alpha. So we're left with negative 1/2 mgl equals 1/3 ml squared alpha. Left hand side, sum of all torques. Right hand side, I alpha. And in this case, there's only one torque, and that's by gravity acting at the center of mass. So some things cancel, which is always nice. One factor of L cancels, and our M's cancel. Doesn't matter what the mass of my hand, mass of my arm is. I didn't have mass written up here, you notice. Doesn't make any difference. So now we can simplify this a little bit more. You get minus 1/2 G equals 1/3 L alpha. So we can solve this for alpha. Alpha equals, let's see, minus 3G over 2L. We have all that information. Equals minus 9.81 meters per second squared divided by 2L, which is 2 times 0.74 meters. And when you do your math, you'll find out that the angular acceleration is equal to minus 19.9. Let me see. I actually should have had a 0 here. 3 significant figures. Okay. So alpha, you do your math, stick your numbers in, you get minus 19.9 radians per second squared. There you go. That is your alpha. It's negative because it's going in a clockwise sense. Now, what is the tangential acceleration? Well, that's just a matter of plugging in. Tangential acceleration is equal to minus r alpha. Okay, and what we're looking for here, as I said, is the tangential acceleration of my hand way out here. So r is just equal to 0.74. It's equal to L. So that's going to be equal to, there should be no negative sign there. I'm not sure why I put a negative sign there. Acceleration, tangential acceleration is r alpha. R is just going to be L alpha because we're asking for the acceleration out here of my hand. The tangential acceleration is not the same all along this. It's 0 over here because that point's staying still, right? It's 0 on this end of my arm, but it's not 0 over here. It increases as you move out. There's a nice picture in the textbook with some dice that showed this to you. What you get here is the tangential acceleration is going to be L, which is 0.740 meters, times the angular acceleration minus 19.9 radians per second squared. End up getting what? You end up getting minus 14.7 meters per second squared. That is our answer for the tangential acceleration. Now it works out well because it's negative and the arm happens to be moving down. Okay, but I'll say a few more words about the negative signs in a few minutes, but you can't always count on the signs working out that well. All right, like I said, the tangential acceleration is negative because it's going in the direction we would call down. Y is down, right? Up is Y positive, down is Y negative. We got a minus sign here because of the minus sign there, but they don't always line up so nicely. I'll say more words about that in a later example. But for now, that's the answer. That's an application of Newton's second law for rotation there for you. Okay? Next up, we're going to see what happens when the sum of all torques equals 0. Turns out it's a very important case. It's called static equilibrium. Up next.